All right, in this problem, we're going to take a look at a classic one-dimensional kinematics problem about a car that's slowing down and coming to a rest. And what I want you to see in this problem is that when we write up a solution in physics for a physics problem, it's not just about getting to the correct numerical answer. Of course, you want to do that. But really, you're trying to tell the story of this problem and show your understanding of all of the concepts that are happening here in this problem. So I kind of want to walk you through my quality solution. It's not a complete quality solution with all of these parts to it like I would like you to write up. But I'm going to show and highlight a few things here. Specifically, we'll just look at a quick pictorial and mathematical representation, and we'll get to some graphs as well. And I'm going to skip doing the word description and evaluation just for brevity in this video. But here's the problem. So we need to go into the text here and take out all the information and then turn it into some pictures and some understanding so we can work through it. A car starts at a position of 1,500 meters, so we have an initial position. It travels to the left, so that's giving us an indication about the direction of motion with an initial speed of 30 meters per second. So we'll make sure to see how to turn that into a correct value for what's called initial velocity. Then the car immediately, so right when the clock reads 0, it immediately begins to slow down at a constant rate. So here we're saying, we're going to have some acceleration value because we're slowing down, and that acceleration will be a constant value. Then the car finally stops at a clock reading of 6 seconds, and we need to determine how far the car travels from the moment it begins to slow down until it comes to a rest. All right, a hint here is to watch out and make sure you pay attention to the positive or negative signs. It's really important here. Cool. So let's take a look at first a simple pictorial representation. And here's what I've done. Um, you could even put some more detail on this, but these are the basics. So we just draw a number line here, and we have our car indicated by this little point particle, and we can see it's traveling to the left with 30 meters per second at a position of 1,500 meters. I've labeled positive is to the right, negative is to the left, and we're going to find out that we'll end up at a final position of 1,410 meters. Now you won't know that when you start the problem, so you would leave this kind of incomplete before moving forwards, but there you go. And then I always want to list our knowns and our unknowns. So this is where we're taking the language of the problem and turning it into some symbols now. So we know that our final clock reading here is going to be 6 seconds. And our initial velocity is negative 30 meters per second. I specifically asked this question by saying it's going to the left to see if you could turn that into negative 30 meters per second and not have a positive there. So watch out. We're going to the left. So our velocity is negative. The problem does not explicitly state that the final velocity is 0 meters per second. You have to figure that out, interpreting the language of coming to a rest. Okay? And then over here, of course, we want to find our final position so we can figure out how far away we are from where we started. So we'll need to determine that. However, we also need to know our acceleration. And this is a real key point. Notice how the problem didn't explicitly ask you to solve for acceleration. You had to critically think to figure that out. Okay, so it's kind of building up the art of solving physics problems and really thinking about what the question is asking. A lot of times it won't tell you to solve for certain things you need to find. You'll have to know to do that yourself. So so then the question is, all right, well then how do we know how to do that, right? Well, that comes down to really knowing the concepts well and then first principles, knowing what are the most basic laws of physics that I need to rely upon so I can work with things and get to the final result. Um, it, in this case, it's the equations of motion, and there's three of them, or at least I use three of them. And you can kind of think of those as the ingredients that we have, kind of the basic ingredients that we want to put together to make some dish, if you will, if you're a cook, right? This is an analogy, right? And so you're doing that, and oftentimes you don't know where you're going to end up, but you kind of weave your way through with the first principles, in this case, the three equations of motion, and then you get to a final answer. All right, so let's see how to do that. And another outcome here is to look at the structure of how I'm doing things. Let me zoom out a little bit so you can see. Um, so first we need to find the acceleration, all right? And I'm writing out without any numbers the first equation of motion, equation of motion number one, to find acceleration. And I'm going to isolate in variables the acceleration first and then plug in my numbers. Notice what I'm doing here, how I'm structuring my solution in the mathematical representation, which is what we are now in. I'm starting with the first principle, the foundational equation I'm going to use. Then I'm solving for the variable I want to solve for, acceleration in this case. I haven't plugged in any numbers yet. It's really important. You want to hold off to the very end as much as you can plugging in numbers. That'll help minimize your mistakes. And then over here on the right, I'm using little bullet points and I'm kind of narrating what I'm doing. I'm helping people understand why I'm doing what I'm doing with the math. This is very key for writing up a quality solution. And as we encounter more complex physics problems, your ability to organize and structure things on the page will benefit you because it'll help you think through the problem. And especially when you're formulating kind of like your final quality solution that you want to communicate to the world, right? You want to organize it and structure it well. Notice also how I'm going downwards in a very straightforward, like linear path to get to these answers. It's not, I don't have all these equations all over the place. I'm going down in a linear way and I'm putting notes to the right over here. All right, so now we have solved for our acceleration. It's a subtraction of our final velocity and our initial velocity divided by the amount of time that has elapsed. And then I can plug in my numbers now. I do that with units to make sure I cancel out my units and everything works perfectly, and I get positive 5 meters per second squared. Watch out, minus and then a minus here, and then you get positive 5 meters per second squared. Make sure you're not falling into a consistent trap where students often think that positive acceleration means speeding up. It certainly doesn't. The sign of acceleration alone tells you nothing about if an object's speeding up or slowing down. You also need to know something about the velocity of the object. Okay, so we've seen that before, and I'm reminding you of that here. Continuing along, now we need to get to the displacement. I asked in the question to find out how far the object travels. So technically, you can just report a positive number, a distance, because I said how far. But to use the equations properly, we will end up getting a displacement, and then you can report that out as well. So I decided to use the third equation of motion here. How do I know to do that? Well, I look at the equation. I say, what do I know? Well, I know my initial velocity, negative 30. I know my final velocity, 0. And I've just solved for acceleration. So I have everything I need, and I can find displacement. You could certainly use the second equation of motion here as well, 1/2 at squared plus the initial velocity times time plus initial position to solve for the final position. That would work too, because you have enough information with time to be able to do that. All right, we keep going. Same structure, organized in a linear fashion downwards, and we're putting notes next to what we're doing. We solve for our displacement, then we plug in our numbers, take care of our signs, square everything, and notice we get a unit cancellation out to give us units in meters, and we get negative 90 meters. So the interpretation here is we have been displaced to the left by 90 meters, and then now you can see over here at 1,410 meters. That would be our final position. So the distance we've traveled, of course, is 90 meters, and our displacement is negative 90 meters in this case. Awesome. We could also put a final velocity of 0 meters per second above here if we wanted to be even more specific on our pictorial diagram. All right, so that's the pictorial and the mathematical, showing you how to structure things nicely as we get to more complex problems. And then finally, let's look at some graphs. So I've drawn out all three graphs here. So here's what you should have obtained. And when I wrote this problem, I kind of chose a poor number for the initial position. That's okay, because it'll help us kind of see something cool here. Because of that, if you actually scaled this from 1500 all the way down to 0 without doing this little like squiggly line, which essentially just says I'm ignoring the scaling here. So like this is 90 meters, but of course from here to here is not 90 meters if it's scaled evenly. So that's what that squiggly line's for. And I tend to not do that in pretty much any physics problem. We always want to scalar things properly. But in this case, I'm doing that because I want to zoom in on just this 90 meters of displacement here so we can see that the position graph is actually curved. If you're way zoomed out, scaled normally all the way to 0, then it'll almost look like a straight line. So Anyways, you're seeing how to do that here. And so looking at our velocity graph, we can see that we start at negative 30 meters per second and we slow down and come to a speed of 0 meters per second, and we have a positive acceleration of 5 meters per second squared. You're again learning hopefully how to interpret these graphs, but by now that should make sense to you on why that's the case. And you're seeing again that the slope of a velocity graph is the acceleration. But now, how do we take this velocity graph and turn it into a position graph? Well, you should be familiar with the concept of a tangent line. And if we go at these different points, I've chosen two of them here, and we draw a tangent line, which is a line that intersects a curve just at one point, we can see that the slope of this tangent line would be 0 meters per second. And that indicates a velocity of 0. And over here, the slope of this tangent line, right when we begin, that would be negative 30 meters per second. And those are our instantaneous velocities at these moments in time. And of course, you could do it here as well. You could, in the middle somewhere, you could draw a tangent line, and you get something in between, like maybe negative 15 meters per second, and then maybe negative 10 meters per second as it starts to shallow out as we're slowing down. Now, these slopes would all be negative, of course, which means we're moving in the negative direction. All right, so there you go. There is part of a quality solution here for this problem of a car that is slowing down. Hope you got some insight there, and you can check your work to see how you were able to do and how you were able to turn all of these words right into a really nice solution that demonstrates your understanding of this physics. With that, take care, and we'll see you in the next video.